two variables, then we're going to go back to our known information that's over here, and we're going to isolate one of those variables. Now, if I look at this known equation right here, then I see that I could isolate h, or I could isolate r, but honestly it looks like it's a lot easier to isolate h, so let's do that. I'm going to go over to the side right here. Let's just divide everybody by pi r squared. Those will cancel, and we get h equals 20 over pi r squared. Whew. Now we can take this and substitute it in for h right there. So we end up with p equals 20 pi r squared plus 16 pi r. In place of h, I'm going to put what h is equal to, 20 over pi r squared. Now that we have our equation in just one variable, in just terms of r, we're ready to do our first derivative test. I like to try to simplify this a little bit if possible, so let's do some cancelage over here on this part. I notice that this pi and this pi cancel. I also notice that this r cancels with one of those guys. So that's going to leave us on the side with our 20 pi r squared plus, now I have 16 times the 20 over here. That's going to give me a total of 320 over, and I still have one r in the denominator. Now I'm actually going to rewrite this part right here as 320 r to the negative 1, because that's a little bit easier to take the derivative of. So I end up with p equals 20 pi r squared plus 320 r to the negative 1. Phew. Let's take a derivative of this. We got p prime. We get to use a power rule here, so I have 40 pi r's plus negative 1 times 320 is going to give us negative 320 r raised to the 1 less power, negative 2. Now that we've gotten our derivative, our first derivative test says please take that derivative, set it equal to 0. 40 pi r squared, 40 pi r's minus 320 r to the negative 2. Now, I have absolutely no interest in solving this pink equation right here using algebra, so I'm going to type that into my handy graphics calculator and do second calc 0. When I do that, I discover that r is equal to 1.3655. Okay, so use your calculator, type in this pink stuff. Make sure you can get to r equals 1.3655. When I look at my derivative graph, I need to double check and make sure that this r value does actually give me a max or min, so let's make our little sign chart. 1.3655. Looking at my graph on my calculator, I see that just to the left, my graph of the derivative is negative, and just to the right is positive. So fully labeled, I go from decreasing to increasing, and it does seem to be the case. Yep, I have a minimum at 1.3655. Now let's go back to the problem in the beginning, and let's see what they actually asked us for. So in this problem, it says find the radius. Check, we've done that. Oh, and the height. So now that we've found the radius down here in blue, we need to find the height. So let's take this radius and let's substitute it into our height equation over here. We know that h equals 20 over pi r squared. When I substitute in my radius of 1.3665, squared, that's going to give me a height of about 3.414. So now we have found our radius and we have found our height. I have one thing I want to point out before we leave this problem. You guys may have noticed that for my radius right here, I went out to 4 decimal places. Now typically in calculus our answers have to be accurate to 3. The reason that I went to 4 on my radius is because I knew I was about to have to plug it in to find the height. And sometimes if you round in the middle to 3 decimal places, it'll make your height wrong to the 3rd decimal place. So I usually go out 1 more decimal place here so that my answer for height is also accurate to 3 decimal places. So watch out for that trick. There's one more type of classic problem that we're going to take a look at together, and it's a problem where you have something happening on a coordinate curve. So this problem asks us to find the area of the largest rectangle. There's our optimization. We're going to maximize the area that can be inscribed, stuck inside, the region enclosed by these 2 graphs. So we have an upside down parabola and a right side up parabola. I'm going to go ahead and label those parabolas so I know which is which. This one is upside down, so that has to be this guy, the red parabola. Y equals 18 minus x squared. That means the other one is this one, the right side up. Now we're kind of lucky for this problem because we don't have to draw our picture, it's already there. So let's start by making an equation. If we are optimizing area, we need an area formula that we can take the derivative of. Now this guy is a rectangle, and we know that rectangles have an area of length times width. Now for this problem things are slightly different, okay, because the length is this bottom part right here, and we need to be savvy, we need to be clever about how we write that length right here. It's tradition in math for folks to list the distance from the origin out to an x-coordinate right here as x. And what that means is back here is also x. So what we need to do is we need to say that our length, this whole distance across, is actually 2 of these x's. So let's do that. That length is 2 x's. Now the width, this vertical length right here, is actually a difference in y coordinates. So I have a y up here, a red y coordinate, and I have a blue y coordinate down here. And to find the orange distance between these guys, we just have to subtract. So the width on this is the red y minus the blue y. Okay, so the red y value minus the blue y value. Now our general way to write the red y value is actually using this equation right here. So my red y value is actually 18 minus x squared. So let's fill that in. A equals 2 x's times the red y value is 18 minus x squareds. And our blue y value is the blue equation, 2x squareds minus 9. I'm pretty happy because this equation right here is only in terms of one variable. Before I optimize it, before I take the derivative, let's simplify stuff so it's not quite so messy. I got 2 x's. I got 18. I'll do a plus change on these guys. I have negative x squared minus 2 more x squareds, that's negative 3x squareds, plus a 9 because I distributed that negative. I got some like terms. I got negative 3x squareds plus 27, and then let's distribute that 2x. Negative 6x cubed plus 54x's. Now the first derivative test tells us that we need to optimize this by taking the derivative of a. So we have a prime equals, do a power rule here, negative 18x squareds plus 54. Let's take this derivative and set it equal to 0. Feel free to use your calculator, or to do some algebra to solve this. It doesn't matter. Either one is fine. Using your calculator or using some algebra, you're going to get an x value of root 3 and negative root 3. Okay, those of you guys who have decimals, it'll be 1 and change. Now we actually can ignore the negative root 3 because the reason it's there is because this x value in our picture, I have positive root 3 distance and negative root 3 distance. It doesn't change our answer. Okay, so I'm just going to focus on the positive one. Let's put it on a sign chart real fast just to confirm that it is in fact the max, not a min. Root 3 is between 1 and 2. If I look just to the left, I notice that my derivative is positive. Just to the right, my derivative is negative. I'm going to fully label it. And yep, it does look like I have a little max at root 3. Last but not least, we need to figure out what in the heck they actually wanted us to find. So let's go back to the problem. It says find the actual area, and what we have found is the x value, half the length of this side right here. So let's take this x value of root 3. Let's substitute it into our area formula up here. I'm going to use my simplified version. Not so helpful. And let's do that over here on the side. So I have area equals negative 6 times root 3 cubed plus 54 times root 3. Now y'all know for calculus they don't actually force us to simplify this right here, but just in case it bothers you not to, when you type that in you're going to get about 62 and some change. 62.354. So either the black answer is acceptable or the orange answer. I would encourage you to keep working on practice problems, refer to your Brown textbook if you find that you're struggling, and take heart in knowing that it'll take some time to get comfortable with these, but it is one of those things that does get easier with practice. Promise, cross my heart.